Hello, welcome back to our machine learning course, and today we'll talk about missing value imputation, or what to do when you have missing values in your data. Now, missing values can occur in many different ways. It's of course possible that the data is missing completely at random, right? It's just randomly missing. There's nothing really causing it, it's just missing. Uh, More commonly, we talk about missing at random data, in which case there is something that affects the missingness. For instance, it could be that a sensor is faulty and just intermittently creates missing values or faulty values. Or it could be that you have data from forms that people filled in, but people just randomly missed questions or forgot to fill something out or were distracted by something that introduced missing values in your data. The important thing here is that there is no relationship with the value, right? So if you have a data set and there is a feature missing, the missingness doesn't tell you anything about what the value could be or not. Right? It's just missing because of some external factor, and the fact that it's missing doesn't tell you anything about the value. It's also possible that the data is missing not at random. In this case, there is a systematic missingness. And basically, because something happened that is systematic, it's predictable, and that can be recognized from the values. Right? For instance, it could be that there's a sensor that decays. Right? So say that you have a time series, and a sensor gives you values, say temperature, and suddenly it does flatline. Right? It could produce missing values here, but they're not random. It's because the sensor broke. Right? In other cases where you have a study with different people, say a medical study, and suddenly people leave the study. Now, this could be because people became very healthy and just stopped coming to the study, or it could be that they got really sick and that they could even die. So in that case, that also affects your data. In these cases, we should not always handle this as missing data. This should be seen as more of a defect in your data that deserves attention, that possibly deserves even special modeling, right? So if, for instance, in medical studies, it's quite common for people to leave. So you should not ignore the fact that people are not anymore in your data. You should really model that into your model. Okay, now missingness can occur in data sets in many different ways. It could be that there is a question mark in your data, could be a -1, could be a string unknown, could be a string NA, could be anything else. It could even be a combination of them, like some missing values have a question mark, some missing values have -1, and so on. So the first thing is, well, to recognize how missingness is encoded or how it occurs in your data set, and that's a very complicated thing to do. There are heuristics for that, but of course, there's no real fail-safe way for this. And finally, it's possible that data is missing in your data X. But it's also possible that there is data missing in your labels Y. So in that case, well, there's two things you can do. You can either just remove that example from your dataset, or if you can't do that, or you should not do that, you can use semi-supervised learning. So these are special learning techniques that can handle missingness in the data. Right? They will typically use that in some way to learn more about the space. So say you have positive and negative points. If you have a point here, you don't know really whether this is positive or negative. But if you know that there's a whole bunch of unlabeled points in this space, and another bunch of points in this space, then, well, this tends to suggest that this is possibly a positive point here. So you use the unlabeled data to learn more about what the distribution of your data is. Okay. Now, there are many imputation techniques. We'll cover the most commonly used ones. And the first one of that is mean or constant imputation. So there we just replace a feature with, for instance, the mean of all the values in the column. we can use k-nearest neighbors. So here we look at if you have a missing data point, which are the points nearby, and then we fill in the value based on that. We can look at iterative technique or model-based imputation techniques. So in this case, you build a model um, on imputed data, and you use that model to predict the value for missing values, and you repeat doing that increasingly, getting better estimates of what the missing data points should be. We'll come back to that, of course. And later we have also matrix factorization techniques. So here we do something called a low-rank approximation. So we decompose the data into two matrices and we join them again, and that will then fill in the data points. Okay, let's dive into it. So the first technique is mean imputation. So what we do here, so say that we have a missing data point. So we have our data matrix, and we have some missing point here. What we do is we look at the column that it's in, we compute the mean of all the non-missing values in that column, and we fill in the mean into every case where we had this missing value there. Okay. In this example here, we take the iris data set. So we have the three classes of irises, red, green, and blue. And we have, for instance, here a missing point. Now, we don't know where this point lies here. So we know that for x2, the value is something like 0.6, but we don't know the value for x1. Right? And now we fill in the value for x1 by taking the mean of all these values, and the mean of that is, of course, here. And then we fill in that mean value, and this brings a point here. And so we do that for all the missing points. And so all the missing points where x1 is missing end up on this line here, and all the points where x2 is missing, they end up on the mean of x2 here. Right? Now, this is a very often used technique because it's so simple to use. But looking at this figure, you can see that it's not even close to where you would expect the data to be, right? So on average, it's not a very trustworthy technique to use. If you have categorical data, instead of the mean or the median, right, depends. So if you expect many outliers, the median is better. If you expect more like a normal distribution, then the mean is better. For categorical values, you just use the most frequent category, right? So you have colors, red, green, blue. If blue is much more frequent, then you replace with blue. Okay. You could also replace with a constant value, so you can choose to replace by 0 if you want to, if it makes sense. Or if it's a text feature, for instance, you can just have a text missing in there. That often makes sense as well. Now, what you can also do is to not lose the information about the missingness, because sometimes, well, missingness can mean something, right? And we don't want to throw away that information. So what we do in this case, if we have a missing value here and here, we add a new, let's call an indicator column. So say that this x2, then we add something like an x2 indicator, and we put a 1 when the feature was missing and 0 otherwise. Right? And this is a new feature that we add so that we keep the information about which data points were missing. That's often a good thing to do. It doesn't always help you, but it's often when you think that it's important to know which points are missing. Yeah, I would definitely advise doing that. Okay, our next technique is KNN imputation. So let's look at that. So say again, I have my matrix. I have a missing data point. And what I do now is I look at other rows in my data set. And so say this is feature xi. Then I will look for the nearest neighbors in the row. Now, of course, I have a problem because I have missing values, so I cannot compute the normal Euclidean distance. Now what happens here is that we use a special distance metric which can handle missing values. For instance, by just ignoring that this feature in the sum of the square distances. And okay, so when you have that, you can compute the nearest neighbors. So say that this one and this one are the nearest neighbors. And what we then do is we look at the values that they have for a missing column, and we replace this missing value by the mean of its neighbors. Right? So if you do that, then you see in this image here, you get pretty good estimates. I mean, at least for this data set, these estimates look pretty reasonable. Right? It doesn't seem to distort the data, at least in any way. And if you look at the accuracy, it's also much higher than we had before with the mean imputation. The next method is called, well, generally it's better known as MICE. And so MICE stands for Multiple Imputation by Chained Equations. It's quite a mouthful. It's also often called iterative or model-based imputation. So what that does, say you have a matrix and you have a feature here which has maybe one or two missing values. Now what you do is, first of all, you replace all the missing values by a first guess of the missing value. You could, for instance, use the mean of the features, right? That's your first guess of all the means. Then what you do is you train a model, for instance, random forest, on all the data except for this one feature. You then, after you fit the random forest, you then predict the values in this column, and this will then give you an estimate of what the missing values are for these two missing values. Okay. Then you repeat, right? So then we look at the next column, and we train a random forest at all the other columns. Now this one is left out, right? So we train a random forest on these ones and these ones, and then we predict this column, assuming that there's a missing value there, right? And we proceed doing that in a round-robin fashion every time, building a random forest on all but one of the features, and then using that to predict the missing values in the features. Right? And the idea is that the starting from a mean imputed value, that's a good enough guess to start training the model, and every time you make new predictions, they will be better and better and better. Or better. Oh well, you don't really know, but you assume that these will be following the distribution that you assume is in the data. Okay? And if you look at the results here, you can see again that these are, well, quite reasonable. The data points are where you would expect them looking at this data set. Performance is slightly lower, but it's a small data set, so I wouldn't pay attention to like 1% difference. Another technique that's often used, is a bit slower, is matrix factorization. So what you do there is you take your data X, as this is an n by p matrix, right? N rows, p features, and you compute what's called factorization. So you have a matrix U, which has n rows and r columns. So R, the dimensionality or the rank, is something that you choose. Okay, and then the matrix V will be an R by P matrix. Right? So the idea is that X equals U times V in matrix multiplication. Right? So this means that if we have some data point xij equals the row of U here, so that's UI times Vj, and j is a jth column here, right? So you multiply these two vectors, and that gives you the value for xij. The way that you construct this decomposition, there's different ways of doing that. The most commonly used way today is gradient descent. So basically you define a loss function over the point x, and basically you measure whether this learned value is close to the real value. I don't know the exact formula, but it's probably something like this, where you compute how good this prediction is. And then you use gradient descent to minimize this loss function. And that gives you then the matrices U and V. Now the good thing is, after you've computed U and V, all you have to do is multiply them. You get a new matrix X, and in this matrix X, all the values will be filled in, and you have no more missing values. Okay. If you look at the results here on the RZA set, you can see it's a bit more spread out. And so it's a different result. It's a slightly lower performance in this case, but it's definitely a valid technique that's useful in many cases. And finally, we have this technique. It's called soft-thresholded singular value decomposition. It also computes a matrix factorization, but in this case, we use the singular value decomposition, which you probably know from high school. So we have matrix X, we have a matrix U, we have a matrix sigma, which is a diagonal matrix with all eigenvalues lambda on the diagonal, right? And we have matrix V. Okay. Again, we can compute this decomposition using gradient descent. The difference is that, so a normal low-rank approximation would take this matrix here. So we have here our eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4. And a low-rank approximation would basically say every lambda value larger than 3, if we use rank 3, we set all these to 0. So all these values become 0. You can do that. In this case, we use something called soft thresholding. And that means that instead of setting these to 0, what we do is we update the value of these eigenvalues with a shrinkage factor or a learning rate, S. And so every time these lambdas will get smaller up to some point, and this will then gradually go towards an optimal solution that you want to use. Okay. And after you've done that, you then recompute x again using x times u times v. And again, the missing values will be imputed here. And you repeat that for m iterations, right? So you shrink the eigenvectors, you recompute x, you redecompose x again, you shrink the eigenvalues again, you recompute x, you redecompose it, and you keep doing it for m iterations. And then you're done. And if you look at the results here, you can see that, yeah, this also gives you nice results. They're closer to where the other points are, which is probably a good thing. And the performance is also higher. Now, which of these techniques works best? On the whole, I think that generally the most popular technique is iterative imputation, or mice. It works quite well for many cases where you have either missing at random or missing completely at random data. It is not the fastest technique, right? So it can be slow. You also have to choose your prediction model, like your random forest. So random forest can be a bit slow here. But overall, this is not a major concern unless you have a huge data set. Low-rank approximations, they're typically, well, they're designed for very large data sets. So yeah, if you have very large data sets, then it's probably a good idea to think about these measures, these methods. Okay, yeah, we've looked at the performance already a bit. So mean imputation gives you, in this case, 91% accuracy. KNN does a lot better, says 97% accuracy. Iterative approach takes a bit longer. I think it was slightly less good. Yeah, 96. Well, it's like half a percentage point. But you can see that it's lower, right? It's a bit faster with Bayesian rich. So that's a linear model, so it's much faster to compute. And also gives you good results. You can do soft compute, which is very fast. Get the same performance, and matrix factorization, also quite fast. It's a bit slower. Yeah, this is a bit worse. Okay, so now how do you use these in practice? So scikit-learn has a number of these implemented. First of all, there's a simple imputer. Just call it like that. You have to choose your strategy, so replace by the mean or the median, or if it's categorical, you can replace it with the most frequent value. You have to say which is the form of the missing value. So if you have a numpy array, this will typically be NP-men, but of course it could be something else, right? If you know that your data is in such a shape that the missing values are encoded by -1, you just fill in -1 here. And this tells the method whether to add an indicator column or not. And then you just call fit transform and you're done. And now your data is complete. So this is typically the first step in every scikit-learn pipeline where you expect missing data, because the imputers are the only method in scikit-learn that can actually handle missing data. Any other component will just quit with an error. So this is typically the first component in your pipeline. So instead of the simple imputer, you can also replace that with the KNN imputer. You only have to choose the number of neighbors, and you're done. You can use that. You can also use this very good iterative imputer. This is currently an experimental feature, but I think it's already quite robust. You have to choose your estimator that you use to build your temporal models. Random forest classifier is used a lot. The default is, however, Bayesian rich. That's historical on one hand, also it's quite fast, and it also gives you quite good results. This says that you have to repeat this iterations for 10 times. And then you do fit transform again. Now, these are the only ones that are currently in scikit-learn. If you want to use the others, you have to use an other package called fancy impute. Now, the problem with this is that this does not fully implement the fit transform paradigm. So you cannot use it in pipelines. You cannot use it inside grid search CV or anything like that. It has a fit transform, but it doesn't have a transform function. So yeah, if you put it in a pipeline, it will fail at some point. The techniques that we have in here are first soft impute. So the fact that not in a CV pipeline is, of course, annoying. So it means that you will have to impute your missing values beforehand, before you give it to the pipeline. That's not ideal, but in many cases, it's not the worst thing in the world either. Okay, so the first method that we can use is soft impute. That's the soft thresholded SVD. Here you have to choose your gradient parameters, like the maximum of iterations, and the shrinkage values for the eigenvectors. The default is 1 over the number of data points. And yeah, you can just call that. You can call fit transform. A fit transform will then produce your filled-in data matrix X. Sorry. And finally, there's the low-rank imputation matrix factorization. Yeah, you have to choose the rank here. You have to choose the gain descent parameters like learning rate and number of epochs, and you can use it as any other method. And you're done. There are actually maybe 5 different variants of this technique. Yeah, these are sometimes faster, sometimes less fast. It really depends on your scenario. All right, that's it for missing value imputation. I hope you enjoyed the lecture and hope to see you next time.